Now that we have a review of derivatives, we're going to take a look at these things called partial derivatives. When we take derivatives of multivariable functions of the form z equals f of both x and y, so two inputs, we have x and y as our inputs, z is our output. We want to know how the output f, or we could alternatively say z, how that changes when only one of the inputs x or y changes. We've already kind of established the fact that if you change both quantities at the same time, it's hard to know how much each input contributed to the overall effect of the output. We treat the other variable as if it were a constant, because we're going to be holding it constant so that we can understand just how a change in one of those inputs causes a change in the output. So this process is called taking a partial derivative. You're taking a derivative with respect to only one of the variables. Instead of using df dx to indicate the derivative with respect to x, we use this alternative notation, which you can just sort of read as the partial of f with respect, I'll just write that wrt with respect to x. Partial of f with respect to x. The reason we use this alternative notation is just to emphasize to someone reading our work that f is a multivariable function. So it means the same thing as df dx, but it just emphasizes that f is a multivariable function. Thus, we have two possible partial derivatives with two inputs. We have the derivative of f with respect to x, and we have the derivative of f with respect to y. Now, we can't write f prime of xy, and the reason is because that makes it unclear which input we're taking the derivative with respect to. So instead of using prime in this alternative notation, we use f sub x and f sub y to denote the derivative with respect to x or y. That's the main difference here. Now let's take a look at an example and revisit our cost of a moving truck problem. The cost C to rent a moving truck is a function of the number of days, d, that it is rented for, as well as the number of miles, m, the truck is driven for while rented. And we get C of d comma m equals 20d plus 0.5m. How do d and m affect the change in C? Well, we already know that it's $20 per day and 50 cents per mile. But if I want to find the partial derivative of C with respect to d, in other words, what is the cost per day, then I would take the derivatives term by term just like we would in a univariate function. So the derivative of 20d to the first power is 1 times 20 d to the 0 power, or just 20. Now we're treating 0.5m as a constant. This is going to be a constant because we're holding it constant. So in finding dCdt, we're going to hold m constant. And mathematically, that means we're going to treat it as if it were a constant. So let's think about 0.5m as just some number. Well, what's the derivative of a constant? If you take 0.5 and you multiply it by a constant, you get a new constant. And the derivative of a constant is 0. So we get 20 as our result. Put it over 1 to emphasize that it's the change in cost in dollars over the change in distance, which is not distance, days, which is measured in days. And we get $20 per day, as we did when we were doing kind of a less elegant analysis of this. Now to find the partial derivative of cost with respect to m, we're going to treat d as a constant. So that means when we look at this function c of d comma m equals 20d plus 0.5m, we're treating d as if it were a constant, and 20, which is a constant, times another constant is still just a constant. So the derivative of a constant is going to be 0, and the derivative of 0.5m with respect to m is going to be 0.5. So we get 0.5 over 1. 0.5 is in dollars, change in cost, divided by change in miles. And we see once again that we get 50 cents per mile as the partial derivative. So this just means that we now know how every additional daily rental will affect our overall cost. Every day will cost $20. And we know how every additional mile is going to affect our cost. It's going to be 50 cents. Let's just practice taking some partial derivatives here. We're going to find in each of these examples, we're going to find both partial derivatives. So let's focus on df dx first. Now we're not going to give this any context. We're just going to go through the operations. Now this guy doesn't depend on y at all, so we don't even have to worry about treating y as a constant. So I'm just gonna state it here though. Hold y constant. And there is no y, so it's not going to affect our derivative at all. The derivative of 3x is 3. The derivative of 2 is 0. And so we get a partial derivative of 3. If we had units, we would write 3 over 1, put the units of f on top, units of x on the bottom. That would tell us how f changes for every increment of x. Now to get df dy, we're only going to let y vary. We're going to hold x constant. Now when we do that, we have to think about this fact that 3x is a constant times something that we're holding constant. So we have a constant times a constant, which is a constant. And the derivative of a constant is 0. Here we have another plus another constant. Its derivative is 0. And so what we can say here is that changing y by 1 has 0 effect on f, right? In fact, what I could do here is I could say this is 3x plus 0y plus 2. And now you can see that there is a y in there. It just has 0 contribution. And so increasing y from 1 to 2 or 10 to 11 will have no impact on the size of the output of this function. In this second example, let's again find df dx. So how does x influence this function? Well, it doesn't. I'm just going to say hold y constant. And again, you could say this is 3y plus 0x plus 2. And if we're holding y constant, then 3 times a constant will be a constant, and its derivative will be 0. The derivative of 0x is 0. The derivative of the constant 2 is 0. So just like we said up here, changing x by 1 has no impact on the output. Now, the partial of f with respect to y. Well, now I do have a y term in here. The derivative of 3y is 3. The derivative of 2 is 0. And so I get a derivative of 3. Well, now let's inject both of these variables in here. Now this kind of looks like our cost function. It's a linear function. And if I take the derivative of f, and I should have said hold x constant, but since there was no x in there, that just meant that it didn't influence our derivative taking process at all. And df dx, again, means hold y constant. So anywhere you see a y, you're going to treat it as if it were a number. So the derivative of 3x with respect to x is 3. And since y is being held constant, 2 times y will be a constant, and the derivative of a constant will be 0. So we get a derivative of 3. In other words, we can see that every time you increase x by 1, there will be an increase in 3 units of f for every 1 unit change in x. df dy will be the derivative of this with respect to y, so treat x as if it were a constant. So 3 times x will be a constant, and its derivative will be 0. The derivative of 2y with respect to y will be 2. And once again, we see here that every time you increase y by 1, there will be an increase in f of 2 units. So 2 units of f for every 1 unit increase in y. And I like to just put all of these over 1 just to emphasize the fact that we're talking about a 1 unit change in the input variable. Now what happens if we start to have functions that have interactions between x and y like this one? Well, I'm going to kind of go through a similar process here. When I write df dx and I hold y constant, I see that in this equation 3xy plus 2, 3 and y are both being held constant. So let me pull those out and rearrange the order of multiplication. And what that means is that 3y is a constant, and I have a constant times x. Well, what's the derivative of a constant times x? Well, it's the constant, like the derivative of 3x was 3. So in our case, the constant is 3y. And so the derivative of 3yx with respect to x will just be 3y. The derivative of a constant 2 is still 0. And so I get a derivative of 3y over 1. So in this case, the amount by which f will increase kind of depends on what value of y we're currently at. So I do not have a constant rate of change in this function here. To find df dy, I'll do something very similar, but I'll hold x constant. And let me write this again as 3x times y. Since we're holding x constant, that means 3x is a constant. And the derivative of a constant times y with respect to y will be the constant. Just like here, the derivative of 2y was just the constant 2. And plus 2, the derivative of a standalone constant is 0. So my output of this will be 3x over 1. So what this says is that in order to know how much f will change by when I increase y by 1, I need to know the current value of x. As another example, now we have a couple of terms that have an interaction piece. And to find df dx, again, I'm not going to write it now, but I'm going to hold y constant. Maybe I will write it just for emphasis to remind ourselves. And what I'm going to do in rearranging these is if I hold y constant, I'm going to kind of pull all the constants out to the front. So this is 3xy is the same thing as 3y times x. 3xy to the 100th is the same thing as 3y to the 100th times x. Now since we're holding y constant, a constant to the 100th power will still be a constant, and 3 times that will still be a constant. So this whole thing right here is a constant, which means the derivative of a constant times x is the constant. The derivative of a constant times x is the constant, and there is my derivative function. Let's do df dy. We're going to hold x constant. And again, what I'll choose to do here is write this as 3x times y plus 3x times y to the 100th. So anything involving x and any numerical values will be constants. The derivative of a constant times y with respect to y is the constant. Now, here I have a power rule because I have a constant times the derivative of y to the 100th, which is 100 y to the 99th. So this will be 3x plus 300 x y to the 99th. And in this case, you could see that how much f changes by per a 1 unit change in y depends on both the current value of x and the current value of y. We'll do more with this later, but for now we're learning to take the derivatives. And once again, something that looks seemingly kind of complex, but if we apply the same logic to this function, it should not be that much different. So hold y constant. So what I'm going to do here is I'm going to rearrange this as 3 ln y times x, because this is all just multiplication. So that means anything having a y in it is going to be a constant, minus 2y times e to the 3x. And so this will be treated as a constant. So this is no different than taking the derivative of, say, 5x plus 4e to the 3x. The 5 and the 4 would still be multipliers, but we would take the derivative of this part and of this part. Okay, so the derivative of a constant times x is the constant. And then the derivative of the second term will be minus the constant times the derivative of this guy here, which will be, from our rules, it'll be 3e to the 3x. Do some rearranging, I get 3 ln y, and then I have 2 times y times 3 times e to the 3x, so that's minus 6 y e to the 3x. To find the partial of f with respect to y, I go through the same process. We're going to hold x constant. I'll just take a moment to rearrange these terms. I have 3x times the natural log of y, so that's our constant. And now I'll have minus e to the 3x, minus 2e to the 3x times y. So this whole thing, I'll write this as plus, this whole thing right here is a constant. And so now I just have to worry about the derivative of the natural log of y, which is 1 over y. So I get 3x times 1 over y plus the constant, negative 2e to the 3x, times the derivative of y. Well, the derivative of y is, it's 1y to the first. Its derivative will be 1 times 1, which is 1, y to the 0th, which is just 1. So the derivative of y is 1. And I could clean this guy up a little bit more and write this as 3x over y minus 2e to the 3x. And there is our partial derivative. So now we have a basic sense of taking these partial derivatives, and now we're going to move on to actually applying this to meaningful situations.